Okay, so welcome everyone. Sorry for the delay. And today we have a talk by Dmitri Bykov. We'll speak about sigma models. So you can start.
Yeah, that's right. Hi everyone. I don't know if hopefully you can see me. So yeah, I'll be speaking about sigma models interpreted as Gross-Neveu models. I really hope you can see what I'm writing. Can you see anything?
Probably that one is better.
Right. Okay, so sigma models is Gross-Neveu models. So it's based on some work I've been doing in the past maybe couple of years. So well, the relevant papers were mentioned in the abstract or in the announcement. Maybe a couple of you have heard some version of this talk before, so I'll try to change that a little bit the exposition and concentrate more on the supersymmetric setup in the second part of the talk. So the plan is that I will introduce the CPN model as a main example, where one can motivate the equivalence with Gross-Neveu models. So CPN model, I interpret it as a Gross-Neveu model. So it's some concrete reformulation of the model, an explicit correspondence. So it's not even a duality or anything. It's just an explicit rewriting, so to speak. And then in the second part of the talk, I'll concentrate on the supersymmetry. 2.2, so as usual, CPN model. Maybe I'll mention briefly how general this construction is, and there are other models with complex homogeneous target spaces and their deformations that can all be put in this framework. But this is like an easy enough and clear enough example, so we will mostly concentrate on that. Okay, so maybe as an announcement, I'll just mention that since the claims that the CPN model, for example, is equivalent to a Gross-Neveu model, that means that sigma models of this type are actually polynomial models, so models with polynomial interactions, which seems like unlikely or curious if you start from the usual setup with constraints, with quadratic constraints, and so on. So actually, all those constraints can be explicitly solved, and the model becomes a model with polynomial interactions, bounded degree polynomials, and so on. We'll start. So we'll start with the CPN model, like I said, and more exactly, it's actually easier to start with the Gross-Neveu model and then perform some transformations and then see that it's equivalent to a CPN model. So the Gross-Neveu model, as you know, has been known since the 70s. I think about maybe 1974 or something like that plus. So the Gross-Neveu model has the following logrange. Again, I hope that people online can see something.
We can see.
Yeah?
Yes.
Great. So this is the kinetic term, some constant, and the interaction. So this is the Gross-Neveu model. More exactly, this is what is called a chiral Gross-Neveu model. Chiral and gauged. So chiral means, of course, that there are these chiral projectors here in the interaction term. So there are the chiral projectors. So in principle, a priori, no one tells us that we should insert chiral projectors. We could as well put arbitrary linear combinations. But this is I'll explain how chirality works here. And gauge means that there is a gauge. Obviously, here there is a covariant derivative, which here it's a U1 kind of gauge field. So deep psi A is where dmu is dmu plus by a mu. It's a U1 gauge field, or actually it's more appropriately to call it a C star gauge field. So U1 / C star gauge field. Of course, if you say consider Grassmannian models and so on, you will have other gauge fields, non-abelian, for example. So this is simple enough. Okay, so now the idea is to rewrite this thing in components, first of all. So this is, I hope, a familiar setup, so I'll erase it for the moment.
So is it the Lorentz invariant? Right?
Yeah, it's Lorentz invariant. Sure, Lorentz invariant, and but I will consider mostly Euclidean signature. Actually, exclusively Euclidean worldsheet signature here. Worldsheet. And presumably it can be generalized to Riemann surfaces and so on, but you can think of the simplest Riemann surface that you can imagine, whatever C or cylinder, C star, something like that. So this will not be part of the discussion today. Yeah, so the A indices are, so there's a number of species of these fields, yeah, let's call them fields. So they just run from 1 to n. So meaning that Cpn minus 1, we want to have Cpn minus 1, so we should have SUN symmetry, right? So these are just the usual n of SUN. Yeah, so I should mention that this is, of course, the stuff that was considered since the 70s, but usually what one considered is the fermionic Gross-Neveu model. So where the fields psi are fermions. Here, however, I will insist that these are bosonic variables. So just kind of for the moment, take it at face value. These are just bosonic meaning commuting variables. So actually, I will call it the Dirac boson. So just like you have a Dirac fermion, we will have a Dirac boson. So in 2 dimensions, it has two wild components, and we will now split this whole Lagrangian into wild components, and we will see what it gives us. So the wild components are psi is decomposed as U and V. So there is an A index everywhere, if you like. Or collectively speaking, this U and V each belongs to Cn. Has n components. And the Lagrangian can be written as V d bar U plus U bar dV bar plus kappa U bar U V bar V. Well, the nice feature of this Lagrangian is that it's quadratic in either U or V, right? And this is a feature that's actually guaranteed by chiral symmetry, which is the reason why I wanted to have a chiral model. So there is a chiral symmetry here, chiral symmetry, which sends U to lambda U and V to lambda inverse V, where lambda is an arbitrary complex number. So, sorry, I want to put a bar here. It's actually important. Sorry. So the point is that if lambda was a phase, right? Lambda inverse bar can transform exactly like lambda. So this would be just a charge transformation, sending psi to psi times a phase. So this would be the usual vectorial transformation. Whereas when lambda is a complex number, this is a chiral transformation. So when it's not a phase. Yeah. So this is actually a feature of Euclidean signature, that in Euclidean signature, chiral transformations work like complexifications of the usual transformations. So in Minkowski's signature, we would have U1 times U1 instead, but here we have complexification of U1, which is C star. That's the kind of reality properties of the fields in Euclidean signature.
So just to check, U bar is the complex conjugate of U, and V bar is.
Yes. V bar is a complex conjugate of V.
Okay, thanks.
Yeah, this is a bar. This is not a separator, right? It's a bar over V. Yeah, and so now you see that the interaction term is invariant as well, because U bar U is multiplied by an absolute value of lambda, not squared, and V bar V is multiplied by absolute value of lambda inverse squared. So they cancel out. So from first principles, if we didn't insist on chirality, we wouldn't be able to exclude terms like U bar U to the fourth. So there's nothing wrong with these terms in principle, or V bar V to the fourth. So they are U1 invariant, but not C star invariant. So they're not chiral invariant. And we don't want these terms because the Lagrangian won't be quadratic and used for these anymore if we add those terms, or if it's both of those terms, let's say. So this is one reason why we want chirality, and now I'll explain why actually we want the Lagrangian to be quadratic in the fields. Is because of course we want to eliminate these fields by a quadratic transformation. Usually integrate out a quadratic variable in the Lagrangian.
Sorry, why you cannot take like powers of U bar, V bar, higher powers? It's still
yeah, it's still invariant. I think it will not be renormalizable, right? In that case, I mean, I suppose if you include some higher powers, this will lead to an infinite number of higher powers. But well, I didn't explicitly check it. But this is the usual kind of quartic interaction in 2 dimensions that one has for fermions, so it's natural to extrapolate it to bosons also. So the idea now is to eliminate either U or V. It doesn't matter which one you eliminate, but just for definitiveness, I'll eliminate V. So eliminate V. And then you get a Lagrangian like this. So L is 1 over kappa, du bar, d bar U, over U bar U. So dot means scalar product with respect to the SUM indices. Yeah. And actually, maybe it looks a bit funny, but actually it's nothing but the CPM model in the gauge formulation. So this is the CPM model in a GLSM formulation. And how can one see that? Well, you see, this is yeah. I should say that the original Lagrangian has the C star symmetry is actually local, right? Because there are these C star gauge fields. So when you can perform local C star transformations and compensated by the corresponding gauge transformations of the gauge field. Therefore, this form is also C star gauge invariant, meaning that if you rescale U by lambda, it will the covariant derivative will be rescaled accordingly, and it will cancel against the denominator here. So it's still C star, not just U1 gauge invariant, C star gauge invariant.
So why they call C star? Isn't just C? like all complex numbers?
No. I mean the group of multiplicative complex numbers. Yeah. Yeah, it's a complexification of U1. Yeah. So you take e to the power.
But this gauge symmetry means only that it can be coupled to U1 field in a gauge invariant way, right? Because this the potential is not part of is not in the field content of this model. You need still to add some Maxwell or Young-Mills term, right?
No. This is a GLSM formulation, so it's like auxiliary field. Yeah. So in the GLSM formulation, I just remind that in CPN model you introduce a multiplet of matter fields, which in this case are just n complex fields, and then an additional U1. Well, usually one introduces a U1 gauge field, and then you integrate out the U1 gauge field, and you get the nonlinear form of the model. Yeah, the U1 gauge field in this formulation doesn't have any kinetic term, so it's an auxiliary field, just like here.
Okay, thanks.
Oh, you could as well just look at this Lagrangian here, right? It's algebraic in A in the gauge field. You just integrate out A, and you get the nonlinear form of the CPN model. Yeah. Moreover, the quadratic piece is just A bar A, because U bar U exactly cancels against the denominator. So the usual approach is to set a gauge U bar U equals 1. So the standard formulation is U bar U equals 1. So in this case, we use a projective invariance to set the kind of C star as a radial part and an angular part, right? So we can use the radial part of the gauge symmetry to set U bar U equal to 1. And then we still have a U1 gauge field left. That's the usual formulation. This is a usual way, like we write, say, CPN as a CN without 0, right? Modulo C star. Or we could as well write it as S to n minus 1 modulo U1, right? Hop vibration. So these are two forms, and they're like in a natural way equivalent. So we just use the part of the C star symmetry to set U bar U equal to 1. Then we have a sphere, so a sphere, right? Modulo U1. That's kind of usual formulation. Yeah, in this gauge, what happens is that the denominator vanishes. Well, I mean, is equal to 1, so you just forget about the denominator, and you get just du bar U, which is the gauged form of the CPN model, and 1 over kappa is the radius squared, therefore. Okay, so that's generally the idea, how to rewrite certain sigma models as Gross-Neveu models. The rest is you add more field contents, different gauge fields, and you see what kind of target spaces you can get out of here. This is just to show you maybe that it's actually quantum full, so to speak, so it's not just a rewriting. I'll consider the case of quantum mechanics. So this thing will work in quantum mechanics as well, of course. I mean, you just take the dimensional reduction, replace the dt bar differential by d over dt, and then you get a quantum mechanics with target space CPN minus 1. But actually, this is quite a nice reformulation because, say, even the equation for eigenvalue equation simplifies a lot, and it's by far the easiest way to write the Laplacian on CPN, right? Quantum mechanics on CPN should give you, as a Hamiltonian, the Laplacian on CPN with the Fubini-Studi metric. And then, okay, I just replace this guy d over dt. This is over dt, and that's it. So the canonical quantization just gives you that u, I, and vj are canonical variables. So that means that vj is minus d over duj. And then the Hamiltonian is just this term, right? That's the Hamiltonian. So the Hamiltonian has the form h of psi is sum of u a bar u a. Now I write the sum just to make it completely clear. D of psi duj bar. This is the Houdini Studio Hamiltonian written in this homogeneous coordinates. And that's not all, because we still have the gauge field. We shouldn't forget the gauge field, right? There is a gauge field here, and we should take a variation with respect to the gauge field. And the gauge field says that v times u equals 0, plus, and the same, and an analogous equation for the conjugate variables. So v times u equals 0. So what does that mean? That means upon quantization, right? What does that mean? That means that the sum of ui d over dui acting on psi is 0. And what does that mean in turn? That just means that psi is a homogeneous function of u's, as it should be, because we're working on projective space, right? So it's like a covariant way to impose homogeneity of the wave function. So we don't pass to any kind of stereographic variable where everything becomes complicated and so on. We just work in these homogeneous variables. And moreover, once you impose this constraint, there's no ordering ambiguity here, right? You could ask, perhaps there's an ordering ambiguity in these u's and v's because they don't commute, but the ambiguity is proportional to this constraint. So it actually cancels out. So at least this case is especially neat. That everything is nice. And okay, then it's a question. Say if you want to find eigenvalues of your Laplacian, it's some problem that you need to solve, but it's actually also just for the as a comment, I'll just say that it can be easily computed completely generally here. I am J1 Jm U I1 U I m U bar J1 U bar Jm. And this should be traceless. So these are holomorphic, anti-holomorphic indices. When you contract them, it should be traceless. And this is the general eigenfunction on CPM. And the eigenvalue is also easily calculated. So the eigenvalue is minus m times n plus m minus 1. You just activate this Laplacian, just 2 lines of calculation to find the eigenvalues. And eigenfunctions, of course, are degenerate and so on, like it should be. Anyway, this is just a quantum mechanics application, just to show that even in quantum mechanics, this should be a useful tool. Okay, so now I'll perhaps before passing to the supersymmetry case, I'll mention that one thing that should sound like I say unconventional is that the model is not polynomial, right? We have no hidden constraints actually. We don't have any u bar u equals 1 constraint or anything like that we're used to in sigma models. It's all in this GrossNeveu formulation. There are no additional constraints.
Question.
Mm-hmm.
Suppose you want to compute beta function for CPN model.
Yeah.
So in this formalism, is it easier or what?
Yeah, sure. It's extremely easy, and
you still need to you still need to fix a gauge. So that's where if you're not integrating A out, you need to decide what you do if you want to preserve Lorentz invariance.
Yeah. I think it's some questions that we slightly discussed, right? But well, you could take it as a conjecture that all these models that you can get by gauging GrossNeveu model, they will have the same, at least one loop, they will have the same beta function. How to prove that? That might be more complicated. You could, well, in principle, you could choose a gauge where the gauge field vanishes using the C star symmetry, right?
Yeah.
because if it's not anomalous,
Yes.
so
Yes.
if C star is not anomalous, so C star is a chiral symmetry, so it could be anomalous. Then you could set A equals A bar equals 0. The anomalies are important here. So typically, of course, we expect there to be anomalies for chiral symmetry. So for a model like this, you will have an anomaly. And that you could see already at the level of the free action. So if you drop the interaction term completely, that already has an anomaly. Because this is just a kind of free fermion action, yeah, in bosonic incarnation. And that just gives you a one loop determinant. And we know the effective action is it's kind of abelian Grassmannian theory, yeah. So it's f zz bar 1 over Laplacian f zz bar, and this is not gauge invariant with respect to C star transformations. So this is only invariant with respect to U1. This is precisely proportional to the imaginary part of the variation is proportional to the imaginary part of the transformation. So this model will have an anomaly. But for example, you could add a fermion symmetrically coupled to the gauge field. And that will cancel the determinant and cancel the anomaly. And this will give us CPN models with fermions. So those should not be problematic. And actually, this kind of consideration leads to some conjecture that there is a relation between these chiral anomalies and integrability anomalies in the CPN model. So it's known that the CPN model at the quantum level has an integrability anomaly, which can be cancelled by fermions.
Yeah.
Well, it's a conjecture that chiral anomaly cancellation should be equivalent to that anomaly cancellation in the integrability charges. It was actually observed already in the 80s by people who computed this anomaly cancellation. It was observed that the way the fermion cancels the integrability anomaly is by kind of chiral anomaly diagram. But of course, it could not have been observed that this is related to this kind of chiral anomalies because, well, this bosonic version of the model was apparently not known. So the claim is that the original anomaly is just a bosonic chiral anomaly, and the fermion just cancels the anomaly by usual one loop cancellation. And the coupling shouldn't matter in this argument because this anomaly is a kind of measure-related thing, one loop anomaly. So you could just make a chiral transformation of this V and U variables depending on the gauge field, and it will just drop out of the Lagrange, basically.
Sorry, question. Sorry, even just classically, so aside from anomalies, if you fix this gauge A equals A bar equals
Yeah, sorry, didn't hear you.
0. Now if you integrate at V, sorry, do you hear?
Sorry, the audio is very bad here. So.
Oh, sorry. I think it's my connection. If you fix this gauge A equals A bar equals 0, and now integrate out, say, V, and what you get seems very strange. It seems like now you just have an ungauged sphere. So aside from anomalies, just classically.
Yeah, that's right. Well, it's not an ungauged sphere. It's something like R times a sphere or something like that. But in principle, nothing is wrong with the fact that the beta function could still be the same. So the claim is that the beta function is still the same, even for that ungauged model. There's in principle nothing wrong with the target. So.
Okay, maybe I can ask later. Okay, thanks.
Yeah.
Just to make it kind of for me clear. So in principle, if you have anomaly,
yeah.
In a theory, we're actually integrating over the gauge field. It's not external anomaly, it's internal anomaly. So that means there is some inconsistency.
Yeah. Sure. that means that, well, you're right that it's slightly puzzling, but well, one answer I can find for that is that this is so the usual formulation of the model where you set u bar u equals 1. So you're setting a gauge for a symmetry that is anomalous. You could do that, but your answer will depend on the gauge then, because it's not, the theory is not gauge invariant.
Yes.
Yeah.
So classically, this is fine. At the quantum level, you just get different quantum theories. That's...
You get a different quantum theory, but you see, it's hard to find another gauge which is translationally invariant, SUM invariant. So I suspect it's just the only SUM invariant, translationally invariant gauge that you can find. So if you want to keep those qualities, so to speak, then you should fix that gauge and just postulate that this is the right gauge, although we're dealing with a kind of gauge non-invariant theory.
Okay, yeah, maybe you should move on.
Yeah. Yeah, but actually, a little bit coming back to your original question, another way to compute the beta function is actually to take the variation of this guy, to set the gauge on the matter field. So you shouldn't forget there is the gauge field is a dynamical variable, right? We have to integrate over it, so we have to take a variation with respect to it. And that gives you v times u equals 0, equals v bar times u bar. And we have a C-star symmetry, so we could say set an inhomogeneous gauge. So with the pass to inhomogeneous coordinates, like un equals 1. That's the usual inhomogeneous coordinates on projective space. And then these constraints can be explicitly solved, right? You just solve that Vm is minus the sum over Vi ui, where I goes from 1 to n minus 1. That's why this formulation is better than the usual formulation, because the constraints are polynomial, can be explicitly solved, right? There's no infinite series. And you could as well, you could just plug this into the Lagrangian. The gauge field is no longer there, but you have higher order interactions now. You'll have sextic interactions. And of course, proving renormalizability and so on, like I said, will be more complicated, but it should work if there is an equivalence. And you could compute a beta function in that gauge as well. I have done it in my paper as an exercise, and the one beta function, and it gives the same answer. So that's kind of in support of my previous claim.
But to be still, maybe to be on the safe ground, you just add your fermions, which cancel anomaly, and forget about anomaly.
Yeah, sure. That's what I'm going to do right now, and discuss the supersymmetric model. So in that case, there is no problem. I would like to stress that so now I'll mostly concentrate on the supersymmetric model, but there are other couplings of fermions, for example, minimal couplings and many other couplings that also cancel the anomaly. Like I say, the interaction term doesn't really matter so much, and they can all be put in this setup. So, and I suspect that all kind of quantum integrable generalizations of the bosonic CPN model can be written in this way. That's again a conjecture. But for example, we have minimal couplings. We have supersymmetry. We have say the CPN -1/n model. This is related to the twistor string in the case of CP3/4. All of these can be written in GrossNeveu format. But I'm mostly concentrated on supersymmetry because it's kind of most involved in some sense, but also most interesting, perhaps. So to do the supersymmetry, let's start from the Gross-Neveu model without the interaction. Let's just start from the Gross-Neveu model without the interaction. Already there, you can impose some supersymmetry, it turns out. So I write the following Lagrangian: V d bar u plus u bar d bar. That's the kinetic term without the gauge field, without interaction, without anything. So now let's do a fermionic completion of this guy. This gives this term here plus a fermionic is E d bar C plus C bar dB bar. So these are not fermionic, guys. These are fermions. Again, they are n species of them. These are fermions.
So what's the difference here between bosons and fermions? Because you said that you started from sort of like fermion Lagrangian, but then you said that they are commuting. So
yeah, these are identical.
So the only difference that one.
Yes. Yes.
And why it doesn't lead to problems with quantization? Usually you don't do like proper computation relations for fermion Lagrangians and deformers.
Yeah. Well. Well, at this time, let's say at one loop calculations, there's no problem. What happens in all loops is not yet completely clear. But yeah, I suspect there should be some kind of analytic continuation that should give you eventually the right answer. So I mean, this that's still an open question, I would say, if there is any problem with that. Switching the statistics in this way. Yeah. So these are the fermions. So ultimately, you just have, like you said, the only difference is that there are commuting. So there is a GLN/n symmetry. This Lagrangian is just GLN/n. So there's the only difference. It just leads to n/n kind of. Yeah. The corresponding symmetry transformation has an anti-commuting part. Of course, we don't want this in the supersymmetric CPN model, because we know that in supersymmetric CPN model, all we have is the usual UN, like for the bosonic model, times possibly U1 of R symmetry that will act on the fermions. But still, we want to have UN, not GLN/n. So this is what is called target space supersymmetry, right? So this Lagrangian has target space supersymmetry. Target space supersymmetry. And I'm talking about worldsheet supersymmetry. Yeah, I want to get worldsheet supersymmetry. So how can one do that? Well, first of all, yeah. So apart from target space supersymmetry, actually, this Lagrangian already has worldsheet supersymmetry. This Lagrangian has worldsheet supersymmetry also. It's elementary, and it's du equals epsilon 1c, db equals minus epsilon 1b. Delta c is epsilon to du. Delta v is epsilon to db. So this kind of transformations were considered in this model, this free model, was considered by Augustin in 2005. I think also Castro now 2007 and so on. So you see, there are two parameters. There are two transformations, with epsilon 1 and epsilon 2. The epsilon 1 transformation is part of the target space supersymmetry. It's part of this GLN/n. Then this guy is really a worldsheet supersymmetry because it involves derivatives. And if you take the variation, you see that you have to swap the derivative. So that means it's up to a total derivative, as it should be. And there are two supercharges here, such that with the following property. So each of these transformations is nilpotent, right? So this is q plus squared equals q plus bar squared equals q plus. So q plus with q plus bar equals the derivative. So there is one funny worldsheet transformation, one target space transformation, but their anti-commutator gives a derivative. So altogether, this actually forms a supersymmetry, worldsheet supersymmetry. And these epsilon 1, epsilon 2 parameters are the usual parameters that one eventually has in supersymmetry. So if you look in the 0,2 supersymmetry, there will be 2, 2 once we add the transformations for the conjugated variables. If you look on standard literature, like the book on mirror symmetry, there's some, this section on how supersymmetric transformations work and so on. These are the parameters that feature in these standard transformations, ultimately. But you will see that their transformations that they usually write, they're very complicated. They have some cubic piece also, and so on. So the question is, how does that all appear? So the claim is that this all appears naturally, step by step, once you add a gauge field, once you add the interaction. This will all kind of just starting from these transformations, you can derive that. So the first step, what we want to do is to change the derivative by a covariant. We want to introduce a gauge field and check if these transformations still hold for the free Lagrangian. So let's just introduce here a covariant derivative. Same for the fermions. And you ask, is this still invariant with respect to this transformation? And yeah, of course, we also put covariant derivative. And we ask, is this still invariant with respect to those transformations? And the answer is no. But the variation of this guy.
Dima?
Yes.
Just about names. So what you call target space supersymmetry is really global symmetry, but with in this GLN sense.
Yeah.
It's certainly not, well, it's not Poincare symmetry, but two-dimensional supersymmetry is the normal Poincare supersymmetry.
Yes, yes.
Yeah, well, it's just minor thing. So it's essentially global target space symmetry times two-dimensional supersymmetry, I think.
Not quite, because like I say, this is part of the target space, this guy. So it's some semi-direct product or something. If you just take these transformations, then yes, this is a direct product of. Yeah, I think it's a direct product.
Okay, maybe this is not important. It's very clear. Yeah.
Yes, but yeah. So target space is like in you have PSU 2,2/4 symmetry group in Green-Schwarz formulation of the superstring. So same thing here. You have GLN/M. Yeah? And the worldsheet, yeah, is what we call two-dimensional supersymmetry. Yeah, it's the worldsheet is two-dimensional. That involves derivatives. Yeah, more symmetry. Where the variation of fields involves derivatives. And you get the standard. This is 0,2 supersymmetry algebra. Okay, so now I inserted the gauge fields. I take the variations as is this invariant? No, it's not invariant. So the variation of the Lagrangian is a total derivative, like it should be, plus epsilon 2 times FZZ bar B times U. So FZZ bar is the curvature of the gauge field that we have introduced. Epsilon 2 is this, of course, the parameter of this most relevant supersymmetry transformation. And then we have B times U. So what we do, of course, is we just set B times U to 0. That's a constraint, additional constraint. Let's just set this to 0. And then everything is invariant. If you set this constraint, everything is invariant. What does that mean? It actually means that if you do that, if you set B times U to 0, then secretly you have an additional gauge symmetry in your Lagrangian. An additional gauge symmetry, additional local symmetry, which works as follows. So what should I erase? So there's an additional local symmetry, gauge symmetry, that shifts delta of ZZ bar times U ZZ bar times B. So an additional gauge symmetry emerges because the variation of the Lagrangian with respect to these transformations will be proportional to B times U, which we have set to 0. This is again, this is a fermionic gauge symmetry. This is a fermionic gauge symmetry. Yeah, that's key point. So this is a fermionic parameter. So Grassmannian. So it's a Grassmannian gauge symmetry. Yeah. We're gauging some fermionic group, so to speak. And actually, these two steps, setting b times u to 0, and then observing this additional gauge symmetry, is just a symplectic reduction. So supersymplectic reduction. And this is the same thing that we have with the C star gauge field, with the A gauge field, right? Because if you take variation with respect to A, we get v times u equals 0. And if we just set these constraints, the original Lagrangian without A will have C star gauge symmetry, right? Because the original Lagrangian has v t bar u. If you take the gauge variation, this will give you something proportional to v times u. So that's actually what the gauge field in this kind of Lagrangians does for you. It's just symplectic reduction. The variation with respect to the gauge field gives you a moment map equals to 0. And then when you set the moment map to 0, there's an additional gauge symmetry appearing out of nowhere, which should be. So what we could have actually done, we could have, instead of setting b times u to 0 by hand, we could just add an additional gauge field in the Lagrangian. Super gauge field, and then this would follow from variation with respect to that gauge. So I'll show how this works.
So why is the constraint? This constraint is not symmetric in du to replacing it to CV.
Well, because this is also not symmetric, right?
Yeah, but this is a supersymmetry transformation, and we said this is a condition for gauge inverse, right? For the state. Like this.
No. This is a supersymmetry transformation.
Ah, okay.
Yeah. It's
Excuse me. Also, when you say symplectic reduction, you mean if I go to Hamiltonian formalism, this will be usual reduction by first-class constraints.
Yeah.
So symplectic structure is a Hamiltonian symplectic structure.
Yeah. I mean, this is the Hamiltonian formalism, right? This you could view this Gross-Neveu formalism as a first-order formalism, right? You have the derivatives in the first term plus the Hamiltonian, which is the second term.
Okay, so it is in this sense. Okay,
it is exactly in that sense. The only funny difference here is that here the phase space is complex, right? This v and u variables is like potential bundle to Cn. So it's a complex phase space with symplectic form dv du, right? dv times du. So this is a complex symplectic space, and then we can consider complex symplectic reduction, just like you do for real symplectic reduction. But anyway, I'll just write the complete Lagrangian without the interaction for now, right? We still haven't introduced the interaction, but it's still an interesting theory even without interaction. So L free kind of piece is V. Yeah, so it's V free T times D bar U free T, U bar free T times D V bar. This guy. So U and V are these doublets constructed out of the. So U free T is UC, and V free T is VB. And the gauge field now standing in this covariant derivatives has the form A bar super, which is A bar 0 W bar. So this A bar is just the usual C star gauge field, the one we had before. But now we have a super gauge field W bar. This is all a member of This belongs to SL1/1, sitting inside GLM/M. So we're gauging a super subgroup of SL1/1, triangular in this way. So now everything follows directly. So the B times U constraint follows by variation with respect to W bar. And everything is manifestly gauge invariant with respect to this group. And you can check that there is the worldsheet supersymmetry holds now for this piece. Okay, so the only remaining question is how if the interactions spoil this or not. So the claim is that they don't spoil it. So now we just add interactions in a straightforward way. We just add here kappa trace mu bar. Kappa is the coupling constant we had before, and mu is the moment map. Yeah, but you don't really need to think about it. If you don't want, you don't even have to think about it as a moment map. But you could think as follows. So we have this SL1/1 gauge symmetry. Not SL1/1, but subgroup of SL1/1. So we should of course construct an interaction invariant under that symmetry at least. Mu is the most general expression invariant with respect to GL1/1. So if you ask what is the general expression invariant under GL1/1, you just find mu. It's a matrix, which is U times V minus C times V. This is also a moment map, but you could just look at it as it's a GL1/1 moment map, but you could look at it as just the most general invariant variable, generative function of invariant combinations, GL1/1 invariant. So in particular, it's of course also SL1/1 and also invariant with respect to the gauge. So we can gauge. Interaction doesn't spoil the gauge symmetry. And then you check. So then you check that this guy is also supersymmetric invariant. That involves using the equations of motion. Well, the equations of motion are kind of simple here. So the equations of motion are mu equals commutator mu bar. Kappa. So this is actually a principal chiral model equation of motion. So which is a hint of integrability of these models, and ultimately you show that this model also has a flux pair and so on. It follows from the fact that mu satisfies PCM equation of motion. Actually, it was found in the 70s for the fermionic Gross-Neveu model by there's some paper of Neveu and Papa-Nicolau in the 70s who found that the bilinears in the fermions satisfy integrable equations. It was just an observation. So here it's naturally interpreted as the moment map just for the fermions. Since now everything is super, you could consider also just a purely fermionic piece if you like. So these bilinears are moment maps. And now you use, it's a kind of 2-3 line calculation to show that the variation of the interaction with respect to supersymmetry also vanishes on shell. And then you can show that you can also make an auxiliary transformation so it vanishes off shell. Additional transformation so that it vanishes off shell. Then you just compare those transformations to the ones from the textbook, like I say, and you find all those cubic pieces and so on. They just arise as compensators, so to speak.
So this condition is the condition of invariance, supersymmetry invariance.
This is a consequence of the equations of motion. So of course, equations of motions are for U and V. Mu are functions of U and V. This is the equation of motion for mu, but you use them to check invariance of the interaction term. We know that this is invariant, so this has to be separately invariant. So you check, you use the equation of motion, you swap the derivative and so on, Again, you find that the variation is proportional to some moment map constraints, which are 0. So I'm saying it's kind of Nelson type operation. Yeah, when you do one transformation, then compensating transformation, it all kind of matches up and so on. But it's kind of 2-3 lines. But since there is very little time, I'll just not write it out. Okay, now the last step is, you might ask, how is this related to the usual supersymmetric CPN model? Where is the usual supersymmetric CPN model? And that's that you obtain by imposing a gauge, choosing a gauge. So in the usual supersymmetric model, you don't have the C star symmetry, you have a U1 symmetry, and you don't have this gauge symmetry. So we have to pick two gauges to eliminate this gauge symmetry. You will have the only remaining symmetry, H symmetry, will be the U1, and you will get the usual CPN, supersymmetric CPN model. So more exactly, you do the following. So you pick, so you use the C star gauge symmetry, set U bar U to 1, like we did before. And then you use this local fermionic symmetry to set U bar C equals 0. Because you actually find that this local variation of U bar C is just delta of ZZ bar. So it's just a shift. So clearly by a shift, you can set it to 0. So it's the most natural gauge that you can get here. Because the variation of this will be proportional to U bar U. This is 1, and you will find that delta. So you set these two gauges. And then if you plug the moment map into the interaction curve, you will see that many terms, actually some terms cancel out, the cross terms cancel out because of this condition. That you will get the quartic fermionic piece and the VV bar piece. The V you integrate out, right? And you get the usual supersymmetric CPN Lagrangian, which is 1 over kappa d bar U squared plus theta bar minus kappa theta bar. So theta is the Dirac fermion, of the real normal Dirac fermion. So theta is C B bar. Just like we had psi was U and B bar, right? Remember, theta is C B bar. And you see we have two constraints. So one constraint was B times U equals 0. And the other is U bar C times 0. But these are different constraints. This is a moment map constraint. It is holomorphic because we have holomorphic symplectic forms. Yeah, so this is a moment map. And this is a gauge, like I said. So this is a gauge, and this is not holomorphic. And altogether, these constraints just mean that the U variable is orthogonal to theta. So U bar theta equals 0. And this is the constraint that you find in usual formulations of supersymmetric CPN model, that the boson is orthogonal to the fermion. Like I say, here it splits, if you split this into wild components, it splits into two qualitatively different constraints. One is a moment map, the other is a gauge choice. But it's all kind of natural and so on and so forth. So this is this is most what I want to say, but I want to point out that this whole setup can be also generalized to other couplings of fermions. You could just consider other supersymplectic spaces with other gauge fields, super gauge fields, other moment maps, and you will get different models with fermions. For example, if you consider a moment map for SLN/N symmetry, then you will get a CPN -1/N target space for symmetry. Or you can consider minimal couplings. So it's all the same Lagrangian, just this kind of Lagrangian. The claim you should only care about cancellation of chiral anomalies. That's another question. I just don't have time to discuss it more. Yeah, and then you write this. It's completely canonical moment map coupling. Moreover, you can also consider these deformations, integrable deformation models. You just insert here a classical R matrix. So you just write trace R of mu times mu bar with some parameter. And this will be an integrable deformation. So it's a fairly general setup. But I just chose this example of supersymmetric model because it involves rather a sequence of steps and constraints which naturally fit and so on. So thank you very much.
Thank you. Any questions?
So this is not yet published, or I mean, supersymmetric, or it was published?
Oh, well, it was accepted for publication, but it's on the archive.
Okay.
So can you summarize like the whole idea is to show that like there are two a priori like, different models, and you just show that like after some equivalence transformations, one can be reduced to another, right? Like classes even, like one class can be reduced to another, and for some reason like the one formulation is better than another. So why is it useful?
Well, it's useful because the Gross-Neveu formulation is better than the other. So no, certainly the idea is not to show that there are two formulations that are equivalent. The idea is that this Gross-Neveu formulation should help in the quantum case also, and that this is kind of the morally correct formulation for these kind of models. First of all, because you see, since the 80s there was this problem that there are these integrability anomalies in CPN, in the bosonic CPN model, and there were some ways found to cancel these anomalies by adding fermions. But there were different ways, like minimal fermions, supersymmetric fermions. So it was clear that this is not a supersymmetric phenomenon, that the integrability anomaly cancels. And that's already somewhat interesting, right? So you should be looking for a setup that is not manifestly supersymmetric, not manifestly worldsheet supersymmetric. And this is the setup I'm saying. So because, like I say, here I don't have to consider the supersymmetric thing. I can consider other gaugings, other matter fields that are not necessarily supersymmetric. The minimal case is also easily, minimal fermions is also easily obtained here. And the claim is that, well, the conjecture is that these anomalies are just the chiral anomalies of this theory. So, and the chiral anomalies are just a property of the kinetic, so actually independent of the interaction. So you just pick well, the most general setup is like this. You pick a super phase space with some trace conditions on the gauge group. It's like Westermann-Witten anomaly cancellation condition. Some quadratic conditions on the gauge group that ensures the cancellation of chiral anomalies. So conjecturally, that should lead to a cancellation of integrability anomalies. So all these models should be quantum integrable. Then the interaction curve depends on the moment map. So ultimately on the choice of global symmetry group with which you construct the moment. And those choices in principle could be classified, and you could classify all integrable models in that sense. Yes. But moreover, like I say, I really suspect that this should help in the quantum case, just like I showed you with the quantum mechanics. The quantum mechanics case is by far the easiest way to solve the CPN quantum mechanics model is by doing this rewriting. So I suspect the same should be the two-dimensional case, but that's kind of not done yet. So. And also, there's also another conjecture that it's actually was observed. It's known that dimensional reductions of gravity lead to sigma models with complex target spaces, like CPN, but with Lorentzian signature. So those could also be rewritten in this formula. And these U and V variables will be the Ashtekar variables the dimensionally reduced Ashketer variables. It was actually, well, some simple examples like pure gravity. It's almost certain that that's the case, but in general, it's kind of a conjecture. So yeah, if you put gravity with some vector fields, matter fields, this will give you some more complicated, still complex target spaces. It's also a non-trivial fact that dimensional reduction to gravity gives you sigma models with complex. That goes to Brighton-Warner and so on and so on. Also integrable models.
Does that mean that there is some integrable sector, right?
Yeah, sure. It is this Gerach group, or I mean, this if you review gravity on d-dimensional gravity on d-2 Killing vectors, and get some integrable model. Yeah.
Some other questions? Is it useful for I don't have the
Well, I don't know. Yeah, it would be interesting to obtain some similar formulas for D. But, I don't know. Here you see it somehow relies on the fact that the D and D bar derivatives split. You can split the D bar derivatives by this quadratic transformation, right? How to do that in higher dimensions, where you have more pieces. Right? There'll be like D derivative for 0, 1, 2, 3. Or maybe some twister, I don't know, something related to twister theory. I just don't have a concrete answer.
But if you reduce supergravity on to 2 dimensions, you will not get that supersymmetry, right? You will get something with kind of local.
With what?
With local supersymmetry.
Yeah. I suppose, yes.
Some kind of extra gauging or some, but with fermionic gauge, something like that. Maybe.
Yeah, I haven't looked at it very accurately, but I think I'm pretty sure that qualitatively this it works, but what is that? Yeah, technical. How exactly? Yeah, it's an interesting question for the future. Yeah.
Okay, it seems that we don't have any further questions, so let's thank the speaker. Okay, and good, then see you next time.